Hey everybody, it's Mr. Mott. What we're going to do is go through the heat of combustion of magnesium lab to illustrate Hess's Law. The reaction that we're trying to try to get to today with Hess's Law is a reaction of magnesium plus oxygen to make magnesium oxide. If we were to try to do this experiment in class, and if you look up the temperature at which magnesium burns, you'll see that magnesium burns well above 100 degrees Celsius. And so if we were to try to light magnesium, put it in water, and measure the temperature change of the water, which is typically how we do our calorimetry labs, all the water would boil away. So what we're going to do instead is carry out a couple different reactions to figure out the heat of those reactions, and then we're going to use Hess's Law, add them up, and see what we get. So the reactions we're going to do is reacting magnesium oxide with hydrochloric acid. Second reaction is going to be with magnesium and hydrochloric acid. And we're going to use some thermochemical data from another reaction to help us out. Here's our data, so a big shout out to Joe DiMaria for allowing me to use their data from their lab. We used 100 milliliters or 100 grams of 1 molar hydrochloric acid, and we've got our masses of our magnesium and magnesium oxide in our data table. If you are looking to do this lab, 0.49 or 0.5 grams is roughly 55 centimeters. So we're going to use our Q equals MC delta T formula, and the second part of the equation, however, is taking into consideration our calorimeter constant, which for Joe's group was 38.3 joules per degree Celsius. And you're always multiplying that by your change in temperature of your cold water. Once we convert our joules to kilojoules, we know how much energy in kilojoules the water absorbed. Since no work is being done, our enthalpy of that process was just a negative of that because the heat was released in that process. Next thing we would do is we would calculate our moles of magnesium oxide using molar mass. And then the next thing what we would do is that we would take our enthalpy divided by our moles to get our heat of the reaction per mole. We're going to follow the same process for magnesium. Q equals MC delta T, and we have our temperature change of 20.7 in this one. And using our calorimeter constant, we end up coming out with about 9.453 kilojoules of energy absorbed by the water. And again, we know that the enthalpy of the reaction there is just the negative of that because heat was being released. That's why the temperature of the water went up. We're going to convert our 0.49 grams of magnesium into moles using molar mass, just like before. And then divide those two values to get to our heat released per mole. Those are the values that we're going to be using for our to get to Hess's Law. So what we have is our heats of our experimental data for our heats of reaction for those reactions there per 1 mole, and we're going to use Hess's Law to add those equations up. Add those equations up to get to our top equation. And so what we notice is that our top equation needs to be flipped around. We need to switch our reactants and products so that we have magnesium oxide on the product side. So once we flip it around, notice that we have to change the sign from a negative to a positive when we flip that around. Once we do that, when you add up equations algebraically, anything that's on the same side, like your hydrochloric acid, your hydrogen, your waters, those are all going to cancel out, your magnesium chlorides, and you're going to be left with our reaction, which we have at the top. So once you add those up algebraically, you kind of cancel out the formulas algebraically. We need to add up all of our heats of reactions. And we add those up and we get about negative 618.9 kilojoules. When we look up the accepted value for the heat of formation of magnesium oxide, it's really close to what we got. The accepted value is negative 601.8 kilojoules in the source that I found, which is only a 2.8% difference, which is pretty remarkable just for doing coffee cup calorimetry. Thanks for watching. Hope this helped out. Bye-bye.